Hi, this deck of cards was compiled to facilitate getting through the MCAT-style passage separating enantiomers in a prescription drug. And it mostly deals with general chemistry concepts. Citalopram is a commonly prescribed A-T drug. So what type of drug is citalopram? It's an antidepressant. So this was like a pharmacology question. E-G is when pharmaceutical companies apply for patents on structurally similar drugs to maximize profitability. And drugs that are structurally similar would be like some type of stereoisomer. Okay? So the term for this is evergreening. Evergreening. Which chemical structure, there's not supposed to be an S in structures. Yes, I'll just strike out this X for you. This S. Is the S stereoisomer of citalopram. Now, some people are conceptually flabbergasted by the R and S nomenclature system, and it comes out of the Kahn-Engel-Prelog naming rules. And so R is Latin for rectus, and that means right-handed, or spinning to the right or clockwise, whereas S, as you see right here, is shorthand for the Latin word sinister, which means left or left-handed or counterclockwise, okay? So which chemical structure is the S stereoisomer
this one?
of
I think
citalopram?
it might have been the second one on the previous slide or previous, well, don't look at these as slides, look at them as cards, index cards. So on the front side. And okay, for those of you who still don't know what the heck is going on, so basically you have to decide which group is the highest priority or which group is atomically the heaviest. And so we know it's going to be between these two because double bonds are considered a higher priority over single bonds. And this is the chiral center that we're, concerned with. So if I step out 1 unit of attachment, we're like at the same place. So if I go 1 more unit of attachment, it still looks like we're at the same place on both. So if I venture out again to a 3rd unit of attachment, still looks the same, but aha, now I get a single bond to fluorine and a triple bond to nitrogen. And although you have a triple bond to nitrogen, so you can consider this like 3 ends, fluorine is still heavier than nitrogen. That meaning it has a higher Z on the periodic table. So although this could be considered 3 nitrogens, this is still gonna beat it out. It's like playing rock, paper, scissors because it's just heavier, okay? So that's that. So this is group 1, and then, by default, this is group 2. I think. Actually, this might be group 1. I don't really, actually, no. This is group 1. And then this is group 2. And then this, Okay, I know I'm confusing you. This is group 3. So this oxygen right here is considered group 1. And then this is considered group 2. And then, you're left with this thing. It's considered group 4. I said group 2 over here, but I meant 3. So now we travel in numerical order. So you go from 1, 2, to 3, then to 4. So somehow this turns out to be well, I don't really get it, but you sit down and figure it out. You guys are the ones that need to figure this out, not me. Yeah, but just know that this is how you would name it. Okay? What is carbon's ground state configuration? And when you see a question like this with ground state configuration, it's really asking what is the electron configuration showing the hybrid orbitals. Okay, so you have to expand to show the hybrid orbitals. So what is carbon's ground state configuration? Okay, so that would be 1s2. Remember, carbon has 6 electrons, 2s2. And then you have the valence electrons. So 2px. And remember, this is what a p orbital looks like. So you have it's like figure 8s that meet at the center. So you can consider this, that I'm drawing now, the x orientation, okay? Consider this the y, and if I add a third dimension, you can call that z. So, a dot can occupy each balloon, but since we only have 2 left because carbon has a total of 6 electrons, and there's only 2 left over, we're only going to have 1 occupying half of the x orbital and 1 occupying half of the y orbital. Okay, this might have been in a previous recording. Yeah, I think I went over this before. Oh, I think I just confused you. I said previously, what is carbon's ground state configuration? Now this question is, what is carbon's orbital configuration in a triple bond? An orbital configuration is asking to show the electron configuration in terms of any hybrid orbitals that might be present, whereas ground state just wants you to expand the orbitals for the valence electrons. I'm messing up a lot here, but I think you'll get the point. So remember in a triple bond that carbon is sp-hybridized, meaning it's attached to 2 things, okay? Because you have an S and you have a P, so it's 2 things. And it has 1 triple bond to something. So there's only 1 more bond left to attach to something else. So here it goes. It's 1s. And then you have, this is supposed to be, oh, this looks funny. Well, no, this is correct because you can only attach to 2 things. So this is sp1, another sp1, and then, there's going to be 2 p orbitals left over, okay, and only 1 electron is going to occupy the unhybridized orbitals. So this is carbon's, configuration, the orbital configuration in an sp hybridized bond. Okay, and here goes an sp configuration for carbon that should help you with the previous card.
The central carbon in C single bonded to C, triple bonded to N is sp-hybridized and has a bond angle of blank degrees. So what is this? If we were to visualize this in 3D, what would the bond angle be? And the bond angle would be 180 degrees and it would have like a straight linear configuration. Draw the wedge-dash diagram for RR tartaric acid. So here we go again with this con, angle, prelog, absolute configuration naming stuff. So R, it's R. So whatever tartaric acid is, it's going to have two chiral centers. So two of these four carbons are going to be chiral centers, meaning they're attached to four different things, okay? So this is what it looks like. We have our first chiral center here, and the second one here. And let me see if I can help you out better on this one. This is going to be the highest priority group, and this is second, because you go one out, you're attached to a carbon. If you go one out here, you're attached to a carbon. Then another advancement and attachment, you're attached to an oxygen, whereas another advancement and attachment here, you're attached to this carbon. So this is group 1, this is group 2, this is group 3. Yeah, the rest of the chain is considered a group, and this is 4. You don't really have to worry about 4. Let's just look at this one. So you're going in a counterclockwise fashion. If you go from 1, 2, 3, that's not clockwise, that's counterclockwise. You're going like this. So that would be S. But since the highest priority group is pointing away from you, the H should be over here rather than the OH, you would name this R instead of S. Okay, so don't make that mistake. Now, if we were to do the same thing over here, this is group 1, this is group 2, and this whole thing over here, this whole mess, relative to this chiral center, would be group 3. So now if you travel, you're going in a clockwise fashion, 1, 2, and then over here is 3. So that's R. And we don't have to worry about inverting naming because the lowest priority group is pointing away from you with the dashed line, the hydrogen. So that's just R. You don't have to, rename it as S or anything like that. In the steering wheel configuration of a wedge-dash diagram, the lowest priority group always points away from, toward you. This parentheses is supposed to just come in here, toward. It's supposed to end at toward. Oh, this video, I'm not making it over. So if you love it, great. If you don't, great. You'll still probably learn something. So the answer is, it's going to point away from you. Like right here, like we just saw. Okay? So the lowest priority group should be pointing away from you. And away from is symbolized as a dash, whereas towards you is usually symbolized as a wedge. That's the wedge.